A teaspoon of this star weighs 6 billion tons, and it spins at 20% the speed of light. You could hold it in your hand. If you could survive the gravity, if you could survive the radiation, if you could survive the magnetic field that would rip apart your atoms from 1,000 kilometers away. When a massive star dies, it doesn't disappear. It leaves behind a corpse so dense that a single thimbleful weighs more than all the mountains on Earth combined. This is a neutron star, the universe's ultimate density, the size of a city, the mass of a sun, and some of them are spinning faster than a blender on maximum speed. Some of these dead stars become cosmic lighthouses. They spin and spin and spin, emitting beams of radiation that sweep across the galaxy. We call them pulsars. And some of them become something far more terrifying. The most magnetic objects in the universe. Objects so powerful that they can reach across the galaxy and shake our atmosphere. A neutron star begins its life as a star, a massive star, one with at least 8 times the mass of our sun. For millions of years, it fuses elements, hydrogen to helium, helium to carbon, all the way up to iron. And when it reaches iron, the star is doomed. The core collapses. Protons and electrons are crushed together. They become neutrons. The entire core becomes a single atomic nucleus, a giant ball of neutrons. The outer layers explode, a supernova. For a few weeks, the star outshines its entire galaxy, and what remains is the core, a neutron star. The neutron star is about 20 kilometers across, the size of a city, but it contains more mass than our sun. A single teaspoon of this material weighs 6 billion tons. That's the weight of all the mountains on Earth combined, compressed into a spoon. But here's where it gets even stranger. When the star collapsed, it spun faster. Conservation of angular momentum, a spinning figure skater pulling in their arms. The fastest known neutron star spins at 716 times per second, 716 rotations in a single second. At its equator, it's moving at 24% of the speed of light, 716 rotations per second, 43,000 revolutions per minute. At the equator, 70,000 kilometers per second, 24% of the speed of light. Neutron stars have magnetic fields, trillion Gauss magnetic fields, and when they spin, these fields create beams of radiation. The beams sweep across the sky like a cosmic lighthouse. As they spin, the beams point toward Earth. We see a pulse, then nothing, then another pulse. Radio telescopes detect these pulses. They are so regular that scientists originally thought they were signals from extraterrestrial intelligence. They called them LGM, little green men. In 1967, a young astronomer named Jocelyn Bell Burnell discovered the first pulsar. She saw a signal that repeated every 1.33 seconds. It was so precise that it seemed artificial. Today, we know that pulsars are the most precise clocks in the universe. Some are so regular that they rival atomic clocks. We use them to measure the universe. Astronomers are using pulsars to detect gravitational waves. By timing their pulses, they can measure the ripples in space-time caused by distant black holes colliding. The fastest known pulsar is PSR J7482446 at 716 rotations per second, 43,000 RPM. At its surface, it's moving at 70,000 kilometers per second. At that speed, the pulsar is almost breaking apart. The centrifugal force at the equator is immense. If it spun any faster, it would tear itself apart. The fastest spinning object in the known universe. But pulsars are just the beginning. There's something more terrifying, something that makes pulsars look like toys. Some neutron stars have magnetic fields 1,000 times more powerful than ordinary neutron stars. These are magnetars. Let's talk about scale. Earth's magnetic field, 0.6 Gauss. A common magnet, 100 Gauss. an MRI machine, 70,000 Gauss. A neutron star, 1 trillion Gauss. A magnetar, 1 quadrillion Gauss. 1 quadrillion Gauss, 1,000 trillion times stronger than Earth's magnetic field. A magnetar's magnetic field is so powerful that from halfway to the moon, it would erase every credit card on Earth and suck the pens out of your pocket. A strong magnetic field squeezes atoms in the direction of the field. On a magnetar's surface, atoms would be compressed into long, needle-shaped structures. They would form polymer-like chains across the surface. Atoms would be pulled apart, electron clouds would be stretched, chemistry as we know it would stop working. From 1,000 kilometers away, a magnetar would distort and rip apart all the molecular bonds in your body. You would die, instantly, without knowing why. But the most mind-blowing part? A magnetar's magnetic field is so powerful that it polarizes the vacuum of space itself. Empty space behaves like a prism. Light splits and merges in ways that break normal physics. In 2016, scientists confirmed that magnetars create vacuum polarization. The space around them is not empty. It's filled with virtual particle pairs. It bends light. It breaks physics. Magnetars are so powerful that they change the nature of empty space. December 27, 2004, a magnetar called SGR 180620, located 50,000 light-years away, experienced a starquake. The magnetar's crust shifted. A magnetic reconnection event. A starquake on a cosmic scale. The energy released was beyond anything we had ever seen. The gamma-ray burst traveled across the galaxy for 50,000 years, and when it reached Earth, it was still powerful enough to ionize our atmosphere. For a tenth of a second, the burst released more energy than the sun emits in 150,000 years. The flash of light bounced off the moon. It lit up Earth's upper atmosphere. It was brighter than anything ever detected from beyond our solar system. The apparent magnitude was brighter than a full moon, and it was 100 times more powerful than any previous flare ever observed. NASA's Swift satellite detected the burst. So did RESI. So did radio telescopes around the world. It was a once-in-a-lifetime event for astronomers. Dr. David Palmer of Los Alamos National Laboratory said, "We know of only 2 other giant flares in the past 35 years, and the December event was 100 times more powerful." Dr. Brian Gainsler of the Harvard-Smithsonian Center for Astrophysics said, "The next biggest flare ever seen from any soft gamma repeater was peanuts compared to this incredible December 27th event. The blast disturbed Earth's ionosphere. It created a ripple in our atmosphere that was detected by amateur radio operators. A starquake from 50,000 light-years away reached across the galaxy and shook our atmosphere. 50,000 light-years, that's halfway across the Milky Way. The burst traveled for 50,000 years, and when it arrived, it was still powerful enough to affect our planet." Gensler added, "Had this happened within 10 light-years of us, it would have severely damaged our atmosphere. Fortunately, all the magnetars we know of are much farther away than this. Within 10 light-years, that's the danger zone, and we don't know if there are magnetars hiding in our cosmic backyard. We know of only about a dozen magnetars in our galaxy. There could be millions. They are invisible in visible light. They only reveal themselves when they flare. 1 teaspoon of neutron star material, 6 billion tons, the weight of a mountain, in a spoon. That's 12 million elephants, each one weighing 5 tons, all of them compressed into a teaspoon. The gravity on a neutron star's surface is so intense that if you jumped from a height of 1 meter, you would hit the surface at 4.3 million kilometers per hour. You would be crushed into a thin layer of atoms before you even arrived. If a teaspoon of neutron star material suddenly appeared on Earth, it would fall through the crust. It would bore through the planet, creating a shock wave. It would eventually settle at the center of the Earth, adding 6 billion tons to the core. 1 teaspoon, 6 billion tons, 12 million elephants, 100 Mount Everests. 716 rotations per second, 43,000 RPM, at the equator, 24% of the speed of light. A figure skater spinning at 3 rotations per second, the Earth spinning at 1 rotation per day. A pulsar, 716 rotations per second. The fastest spinning object in the known universe, 43,000 revolutions per minute. Magnetar's magnetic field, 1 quadrillion Gauss, 1,000 trillion times stronger than Earth's, 10 billion times stronger than a lab magnet, 10,000 times stronger than a neutron star, 1,000 trillion times stronger than Earth's magnetic field, powerful enough to bend empty space itself. A neutron star is so dense that protons and electrons are crushed together. They become neutrons. The entire star becomes a single atomic nucleus. The nucleus of an atom has a density of about 2.3 x 1017 kilogauss m3. A neutron star has the same density, but it's the size of a city. A neutron star is a giant atomic nucleus, 20 kilometers across, containing the mass of a sun. The physics inside a neutron star is unknown. We don't know what happens to matter at these densities. The equation of state for neutron star matter is one of the biggest mysteries in physics. Some scientists think that at the very center of the densest neutron stars, matter breaks down into quarks. A quark star, the next stage of collapse. If a neutron star is too heavy, it collapses further. It becomes a quark star. If it's even heavier, it becomes a black hole. The most massive neutron stars are on the edge of becoming black holes. They are gravity's last stand before the abyss. The most massive known neutron star is PSR J09520607. It has 2.35 times the mass of our Sun, and it spins at 709 times per second. There's a limit to how massive a neutron star can be. It's called the Tolman-Oppenheimer-Volkoff limit. Beyond this limit, gravity wins. The neutron star collapses into a black hole. The neutron star is the line between matter and black hole, the edge of what physics can describe. Only about 12 magnetars are known among millions of neutron stars. 4 of them are also soft gamma repeaters. They flare randomly and release gamma rays. The 2004 event reopened a debate. Some short gamma-ray bursts might actually be magnetar flares from nearby galaxies, not black hole-forming explosions from billions of light-years away. Dr. Krissa Kuveliotou of NASA, Marshall Space Flight Center, who coordinated follow-up observations, said, "A sizable percentage of short gamma-ray bursts could be SGR flares." Neil Gehrels, Swift's lead scientist, said, "An answer to the short gamma-ray burst mystery could come any day now that Swift is in orbit. Magnetars are still one of the great mysteries of astrophysics." How do magnetars get their magnetic fields? 2 mechanisms are responsible: the convective dynamo effect, like the movement of Earth's liquid core, and magneto-rotational instability, the interaction between rotation and magnetic fields. Jérôme Guillet of Paris-Saclay University is studying this. His simulations show that the convective dynamo mechanism is the most effective. It can amplify magnetic fields to 10^15 Gauss. His simulations reveal something unexpected. The magnetic dipole moment of magnetars is always perpendicular to the star's rotation axis. Not aligned, perpendicular. The universe is always stranger than we expect. From neutron stars to pulsars to magnetars, each one more extreme than the last, each one pushing the limits of physics. A teaspoon of neutron star weighs 6 billion tons. A magnetar's magnetic field bends empty space. A starquake from 50,000 light-years away shook our atmosphere. We are fragile, The universe is not. We live on a tiny planet, orbiting an ordinary star in a quiet neighborhood of the galaxy, and the universe is full of monsters. In 2004, a starquake from halfway across the galaxy ionized our atmosphere. We didn't feel it. We didn't see it. We only knew because our instruments told us. The universe is not silent. It is full of explosions. We just don't hear them. Every 1.33 seconds, a pulsar somewhere in the galaxy sends a pulse across the universe. It travels for millennia. And we listen. We count the pulses. We measure the universe. 716 times per second, 43,000 times per minute, 24% of the speed of light. These numbers are not just numbers. They are physics. They are the limits of nature. We are the universe understanding itself. Magnetars show us the edge of physics, where matter breaks down, where empty space becomes a prism, where the laws of nature are stretched to their breaking point. In the heart of a magnetar, the universe is still creating, and we are watching. We are the first generation of humans to see these objects, to measure them, to understand them. We are witnessing the edge of the universe. There are millions of neutron stars in our galaxy, each one a remnant of a dead star, each one a cosmic survivor. We are stardust, and so are the monsters. The next time you look at the night sky, remember, some of those stars are dead. They just don't know it yet, and some of them are spinning at 24% of the speed of light. The universe is beautiful, and it is terrifying. A teaspoon of neutron star weighs 6 billion tons. The fastest pulsar spins 716 times per second. The most powerful magnetar bends empty space. The universe is full of extremes. We are the ones trying to understand them. 50,000 years ago, a starquake occurred. 50,000 years later, it reached Earth. And for a tenth of a second, the universe reminded us of its power. The next time you see a teaspoon, a credit card, or a magnet, remember, there are objects in the universe that make them look like toys, and we are just beginning to understand them. The universe is watching. Are we paying attention?